This is a video for AQA Further Pure Mathematics, Calculus section 6.1, which looks at the arc length of a curve in Cartesian form. When we're talking about the length of a line, if the line is a straight line, then it's quite a straightforward method of using Pythagoras' theorem to calculate the length of the line. So, for example, here we can see that the length of line between those 2 points will be the square root of 4 squared plus 8 squared. However, if we have a curve, as in this form, you can see that's not going to be such a straightforward solution. However, there is a method which relies on taking small sections of the curve and saying approximately these are going to be straight lines, and then summing all of those small sections. So this will produce an integral that we can then calculate. This diagram then shows that in a little bit more detail. So this is a small portion of the curve, and we can see that we've got an increment in x there of delta x and a corresponding increase in y of delta y. The arc is then approximately a straight line, so that we can say, using Pythagoras' theorem, that delta s squared will be approximately equal to delta x squared plus delta y squared. So if we then divide through that equation by delta x squared, we get delta s over delta x all squared will be approximately equal to 1 plus delta y divided by delta x all squared. But this is now a limiting thing that we can look at, similar to when you found areas under curves. So we can say that as delta x approaches 0, then delta s over delta x approaches the derivative ds by dx, and similarly delta y by delta x approaches the derivative dy by dx. And hence we have that ds by dx is equal to the square root of 1 plus dy by dx all squared. Now, to find the actual arc length between two values, let's say a and b, we then have to integrate both sides of this equation with respect to x. So that gives that the arc length s will be equal to the integral from x equal to a up to x equal to b of the square root of 1 plus dy by dx all squared dx. So if we've got a function for y, then we can find its derivative dy by dx, substitute into this equation, and then calculate the integral of the resulting equation that we get from that. So let's have a look at that with a specific example then. Here we've got the function y equals 2/3 of the square root of x cubed, evaluated between x is equal to 3 up to x is equal to 8. And we want the arc length between those 2 points. So the first thing we need to calculate is dy by dx. Well, if y is equal to 2/3 the square root of x cubed, that's x to the power 3 over 2. So we get 2/3 multiplied by 3 over 2 x to the power a half, which is just the square root of x. The formula that we want is s is equal to the integral from a to b of the square root of 1 plus dy by dx all squared dx. So we can now substitute the values into that. This will be the integral from 3 up to 8, and then we've got the square root of 1 plus dy by dx all squared is just 1 plus x, and run that dx. We need to now integrate this. This is x to the power a half, so that will integrate to x to the power 3 over 2. So it will become 2/3 of 1 plus x to the power 3 over 2. And that's to be evaluated between 3 and 8. So it's therefore equal to of putting the value 8 into there, 9 to the power 3 over 2, and then minus 2/3 of 4 to the power 3 over 2. And if you evaluate that, you find it's 38 over 3. So there we have then, we had the curve given to us as y equals 2/3 the square root of x cubed. Because the formula is the square root of 1 plus dy by dx squared, we need to find the derivative and square it to substitute into that formula to give us an integral, which hopefully we can integrate by methods that you already know, giving us then an arc length there of 38 over 3. So this was for a case where we've got the function given to us as a function of x. In the next video, we'll look at what happens if we have the equation in terms of a parameter.